Hello, everyone. My name is Sumit. I'm here to present this work, Neural Representation and Latent Space Synthesis of Bidirectional Texture Functions, on behalf of Mandy and Adam, who led this work but couldn't be here in person due to visa issues. Over the next 15 minutes, hopefully I'll convey to you all why this was like such a fun project to be a part of. So in this work, we built a practical pipeline for acquiring real-world bidirectional texture functions, BTFs, and turning them into reusable neural material assets. We built this in like 3 stages. First, we came up with a high-resolution BTF capture setup for complex real-world materials. Then we propose a compact neural BTF representation for accurate reconstruction and rendering. And finally, we invent a hybrid latent space synthesis approach for growing these captured materials into large, seamlessly tileable assets. We chose BTFs to represent our materials because they flexibly encode the spatial angular appearance of real-world surfaces. In contrast, parameterized models like SVBRDFs are popular because they are fast and compact. But these strengths become limitations when modeling materials that are hard to represent with a small set of parameters. Many of the interesting materials we see daily are of this kind, such as woven fabrics with view-dependent color shifts, hand towels with self-shadowing, or car paint with interreflection and glints. So excuse my wordplay, but this is where BTFs shine. This is an example of a sari, which my grandmother and aunts wear all the time. So it was really nice for me to personally share this with them and say, look, I'm working on like what you spend your lives in and so on. So there are many challenges in making BTFs practical, mainly 3. Firstly, high quality BTF data sets are rare. Existing public data sets like UBO 2014 are valuable, but they typically cover smaller spatial regions, so around 6 centimeters square, and low resolutions, so around 512 pixels. Second, raw BTF captures are very large. A capture consists of many HDR images over lighting and viewing directions, so direct tabulation is infeasible. So we need a representation that is compact, but still holds onto the mesoscale structure and view-dependent lighting effects. So I'm going to show an example of what a capture looks like. You'll see that first we'll change the lighting direction, which will alter the shadows on the material. And after that, we'll change the viewing directions. Third, even a great capture is still finite. For design and rendering, we need materials that cover large surfaces, and naively tiling a captured swatch will not give you the desired look. In our setting, standard SVBRDF synthesis approaches don't work because extending a BTF has to preserve the coupling between spatial and angular appearance. So all of this calls for a new approach, and we come up with a unified approach that tries to solve these problems along the capture, representation, and finally synthesis directions. So we introduce a capture setup for high-resolution BTF dataset of complex real-world materials with rich spatial variation and angular effects. We develop an improved neural BTF model that combines multi-resolution neural textures with a 2D view-dependent offset to improve reconstruction over prior neural and parametric representations. Finally, we synthesize new materials directly in the learned latent space of the neural representation. Our hybrid method combines latent Wang tiles and diffusion-based seam healing to produce high-resolution tileable neural material assets. So capture, representation, and synthesis are co-designed to work together in like one pipeline. So here is our pipeline in action. Every fabric you see was like produced and like rendered by our method. 2 things to point out here. The materials marked in like green are rendered directly from our neural BTF fitted to captured data. The ones marked in yellow are extended by our synthesis pipeline into larger tileable assets, such as the carpet. Now let me go into each part of our pipeline in more detail. So for capture, we built a custom goniophotometer. It controls the lighting and viewing directions while imaging the sample, which lets us cover the angular domain a BTF needs. Our capture is carefully calibrated using over around 400 images of a Charuko board with fiducial markers. From images of these markers, we optimize a geometric model of the setup to account for mechanical imperfections. Our dataset contains 17 real-world materials. This set includes leathers, satin, silk, velvets, embroidered textiles, hand towels, and more. For each material, we capture around 1100 HDR images at different lighting and viewing directions, covering rich angularly dependent color variation, specular and glinty highlights, and spatial detail. Here are some more samples from our data set. Beyond fabrics, we also have like car paint seen here in the bottom right. So this is like an example of more flat and angular dependent material with like specular highlights and so on. So after capture, we rectify the raw images with homographies so that points on the reference plane line up across all lighting and view configurations. Any height variation or apparent displacement that remains is handled later by a neural 2D offset module. The raw capture is 6K by 4K pixels. After rectification, the largest regions come out to be 4K by 2.8K pixels over an area that is roughly 28 by 20 centimeters square. For comparison, prior public data sets typically sit around 512 pixel resolution over 6 centimeters square. As you might imagine, this is a large data set. Each raw capture requires about 50 gigabytes, and together with rectified images, it comes up to around like 2 terabytes. And this motivates like the next part of our pipeline, which is like a compact neural representation. A BTF is basically a function that maps surface position and incoming light direction and outgoing view direction to RGB appearance. Our model approximates this function with two main components. The first component is a view-dependent neural offset module inspired by prior work NUMIP. It is designed to absorb parallax from real surface height. Given a surface position and view direction, it predicts a 2D coordinate warp. We use this warp to warp the queried surface coordinates, so the appearance decoder, the subsequent step, samples features at a new location. So like in NUMIP, the basic idea behind the neural offset is that it allows us to model the difference between an assumed planar geometry and the actual microgeometry on the surface. The second component is the appearance decoder. It queries a multi-resolution neural texture pyramid at the warped coordinate, concatenates features across all levels, combines them with the directional encoding to predict RGB appearance via an MLP. We evaluate the neural representation on all 17 materials using held-out lighting and viewing directions. The baselines cover both parametric and neural representations. So in the rightmost column, we have Disney, which is like the widely used parametric model. Then we have NUMIP, which is the closest neural baseline. And NUMIP Plus is a version we scaled up to roughly our model's capacity. So any difference comes from the architecture improvements that we propose, and not just from having more parameters. We have additional comparisons too, but like for those, see our main paper. Our method does better with fine fibers, raised motifs, and angular color shifts. These are cases where BTFs outperform parametric models and where existing neural representations tend to blur or like flatten appearance. We measure reconstruction quality using PSNR, so like the best results are in bold. You can see we win on almost all of them. A compact representation is only useful if you can render with it. We implemented the model in Mitsuba 3 with Dr. JIT using the cooperative vector API, which fuses the network evaluation straight into the path tracer. For an image at 800 pixel resolution at 4 samples per pixel, the unfused implementation on the left takes 140 seconds, and while the fused one on the right takes 0.4 seconds. So beyond compression, you also get a practical renderable neural material. So this is new API in Mitsuba 3, and I would definitely encourage everyone to check it out. The final component is synthesis. Even with like accurate capture and reconstruction, each BTF only covers like a limited region. To use these materials in scenes, we need to extend them to larger spatial extents while preserving their view-dependent appearance. Our appearance features are coupled to the view-dependent offset field, the part that carries mesoscale structure, and the multi-resolution texture pyramid, the part that carries appearance. To keep that coupling intact, we synthesize directly in the learned latent space, so the extended material stays faithful to the capture and still renders as a neural BTF. Our synthesis pipeline starts from the latent stack. This stack concatenates the multi-resolution appearance features and the offset features into one tensor. In our current model, this has like 32 channels. On this latent stack, we apply 2 operations. Our first operation is to build latent Wong tiles. We automatically choose the tile size from the spatial periodicity of the latent stack, then extract latent patches from the captured material and assemble a 16 tile set that can stochastically tile onto a larger plane. To reduce boundary artifacts, we optimize the seams with a minimum cost latent space cut. This seam objective uses both appearance features and offset features, so neighboring tiles agree not only in color-like appearance, but also in view-dependent structure that affects shading. Even with seam optimization, complex materials can still show boundary artifacts. So the second operation we do is diffusion-based seam healing. For each material, we train a diffusion prior on crops from its latent stack. So the model learns that material's local statistics. At synthesis time, we apply in-painting only over the seam regions. So the diffusion prior acts as a constrained local repair. It harmonizes the transitions between tiles without replacing the capture structure that Wong tiling gave us. Here we show the effects of seam healing. The raw Wong tiles are discontinuous in rendered appearance and offset, while the healed versions are not. Here is another example of this. After synthesis, we split the synthesized latent stack back into appearance and offset features and decode them via the original neural BTF network for rendering. Our results show that latent stack is a viable synthesis domain, since not only ours, but like competing methods also produce plausible results. Moreover, the comparison shows where prior approaches fail. So diffusion-only generation captures core statistics, but doesn't preserve structure over large regions. The adapted curved ACF and histogram preserving blending methods are competitive, but struggle with extrapolating over large structured regions. In contrast, our hybrid method uses Wong tiles to preserve structure and tileability and hands off the remaining seam artifacts to diffusion-based in-painting. To summarize, we contribute a unified approach for making BTFs practical by capturing a high-resolution BTF dataset of complex real-world materials, represent them with a compact neural BTF network using multi-resolution neural textures and 2D offsets. Finally, we synthesize large tileable neural BTF assets using latent Wong tiles and diffusion-based seam healing. Our main message is that BTFs don't have to stay niche, bespoke captures used only in like very specialized settings. With the right capture, representation, synthesis, and rendering pipeline, they can become first-class material assets for everyday rendering and design. Thank you. Please see our project page. We are working on releasing our code and data soon, and I'm happy to take any questions.
Questions then?
Thanks for the talk. I have a question about is your method only works for albedo texture or any kind of texture, like normal map or other like?
So this is like a different representation from like render buffers. So like we capture the 6D function of a planar surface for each location for all ingoing and outgoing directions. We capture like RGB appearance. We don't have like normal maps and stuff like that. That's all baked into our neural material representation. So it's not albedo either.
So you mean the lighting, for example, will infect the meso geometry scale? Is it possible?
So light goes into the material, does all complicated things, and then goes out in one direction. We don't explicitly model all the complicated interactions that are happening with the material. We just like record what happens when the light leaves in an outgoing direction, and then learn that transfer function.
I see. Thank you.
Yeah.
Thank you. Can you give some insight about why the SVBRDF baseline is behaving so badly in your experiments?
Right. That's a good question. Because our materials and like real world materials are very complicated, they have all kinds of effects that only a surface-based model can't handle. So for example, our skin has like subsurface scattering where the light goes inside the material and comes out from somewhere else, or like materials have like self-shadowing and interreflections and so on. These effects can't be modeled by SVBRDFs that easily.
I would disagree. But,
okay.
I mean, a lot of modern SVBRDF models do have all those channels part of their description, including mesostructures for the geometric relief, subsurface scattering maps, and a bunch of other stuff. And as long as you have like a physically based rendering engine that runs on them, you can reproduce all those effects. So it looked in the examples that everything was very blurred and a very damaged BRDF model was used.
So are you talking about our results or the BRDF results?
Maybe we can go to that slide if it helps.
Yeah, all those examples on the right, like I really don't understand how you can end up with that kind of result with a properly optimized SVBRDF against the capture that you do.
So we optimize like for example, we optimize like the roughness, metallicity, and all those things per like basically texture maps for each of those against like the viewing direction, like against like our capture using like Adam optimizer. And this is
do you optimize the displacement map?
We optimize the normal map, but not the displacement map.
Okay, because most of the cell shadowing is not here because there is no displacement map, while all modern SVBRDF do have a displacement component.
And it gets blurred because it doesn't align, because of the parallax, no?
I would be surprised. Well, we can take it offline, but...
no, I'm happy to hear. Yeah.
No, we have to say something.
Yeah, so you can reproduce probably the exact same result that I see on the left with a properly optimized SVBRDF that contains displacement maps, subsurface scattering maps, and all the coefficients that you have in a model like OpenPBR or something modern. If this is the 2012 Disney BRDF with no displacement, that's not a proper SVBRDF baseline. That's what I think.
But Neumip has the displacement, Tommy, I think.
So
Neumip has, I think, and it's still blurry, and we're out of time.
Yeah, but this one has no displacement, if I understand.
All right, we agree to disagree,
and
we'll be taken offline. Nothing to be sorry for. No, this is super interesting. Let's thank the speaker again, right?